Hey guys, welcome to the Nightly Science Channel. Today we're stepping quietly toward one of the most unsettling and beautiful questions the universe has ever posed to us. Not with alarms or dramatic warnings, but slowly, gently, as if we're drifting closer to the edge of something vast and unknowable. Picture yourself floating in deep space right now. No up or down, no sound. Just a soft darkness scattered with distant stars, each one humming faintly with age. Ahead of you, almost blending into the black, is something darker than darkness itself. A region where light bends, time hesitates, and every familiar rule you've ever known begins to loosen its grip. This is a black hole, not the violent monster from science fiction, but something quieter, more patient, more absolute, a cosmic prison where matter enters. Information seems to vanish, and our best theories begin to whisper instead of speak. Tonight, we're not rushing in. We're not crossing any lines yet. We're simply standing at the threshold, asking a question humans may never fully answer. What really lies beyond a black hole? Before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Black holes weren't discovered through explosions or glowing trails. They emerged quietly from mathematics, from equations that, when followed to their natural conclusion, pointed to something impossible, a place where gravity doesn't just pull, it overwhelms. A place where space curves so sharply that the future itself points inward. At first, physicists resisted the idea. Surely nature wouldn't allow such an absurd object to exist. Surely the equations must break before reality does. But reality didn't break. Stars collapsed, galaxies formed, and black holes revealed themselves, not by what they emitted, but by what they stole. Light, motion, time, direction. We call them black, not because they are empty, but because they are too full, too dense, too final. And yet, for all their reputation, black holes don't announce themselves with chaos. From a distance, they are serene. Orbiting stars move calmly. Accretion disks glow softly. Entire galaxies revolve around something they cannot see. That quiet is part of what makes them so unsettling. Because once you cross a certain boundary, a surface known as the event horizon, there is no message you can send back. No signal, no echo, no goodbye. Not even light escapes fast enough to report what happens next. It's not a wall. It's not a doorway you feel yourself pass through. It's simply the moment when returning becomes impossible. Outside observers would watch you slow. Your clock would tick more and more gently, stretched by gravity itself. To them, you would never quite cross the horizon at all, frozen forever, fading into darkness. But to you, time would feel normal, and that alone should make you pause. Because it means reality itself disagrees about what happens next. For decades, black holes have stood like silent judges at the edge of physics, exposing a deep fracture in our understanding of the universe. On one side stands Einstein's general relativity, confident and smooth, describing gravity as the graceful curvature of space and time. On the other stands quantum mechanics, jittery and precise, insisting that information is sacred, that nothing ever truly disappears. Black holes obey both, and yet satisfy neither. General relativity predicts a final destination inside, a singularity, a point of infinite density where space collapses into nothing and time loses meaning. A full stop, the end of the story. Quantum mechanics refuses to accept that ending. If information falls into a black hole and vanishes forever, then the universe is not reversible. Cause and effect break. Physics loses its memory. That conflict, quiet, mathematical, unresolved, is known as the black hole information paradox. And it is the reason we are here tonight. Because every attempt to answer what lies beyond a black hole is really an attempt to heal that fracture, to reconcile two descriptions of reality that both work but cannot agree. Some theories suggest tunnels through space-time. Others imagine entire universes blooming on the far side. Some deny that an inside exists at all. And some propose that the black hole, rather than destroying, may be recording everything it consumes, like a cosmic archive written on its surface. Each idea is strange. Each is mathematically serious. None have been proven, yet all of them share one thing in common. They force us to question what we mean by inside, outside, before, and after. As we begin this journey together, it's important to understand that black holes are not just objects. They are boundaries, tests, mirrors held up to our assumptions about space, time, and existence itself. They don't merely hide answers. They ask better questions. And tonight, we'll follow those questions slowly, not to shock or frighten, but to wander calmly through the edges of what science can say and what it can only imagine. Wherever you are, let the world slow down for a while. Soften your gaze, let the hum of life around you fade, and gently drift with us into tonight's quiet exploration. There's a temptation, when thinking about black holes, to imagine them as objects you could point to, like planets, stars, or clouds drifting through space. Something with an edge, a surface, a center you could eventually reach. But a black hole isn't really an object in the ordinary sense. It's a condition of space-time itself. To understand what happens beyond one, we first need to slow down and understand what a black hole actually is. Not as an idea, but as a structure woven directly into the fabric of reality. Imagine a star many times more massive than our sun. For millions or even billions of years, it lives in balance. Gravity pulls inward, trying to crush it. Nuclear fusion pushes outward, holding it up. Light itself becomes a form of resistance. Eventually, that balance fails. When the fuel runs out, gravity wins. The star collapses, not gradually but catastrophically. Its core falls inward faster than light can escape. The mass becomes compressed into a region so dense that space-time curves sharply around it. That curve is not metaphorical. It is literal geometry. According to general relativity, gravity is not a force pulling objects together. It is the shape of space-time telling matter how to move. And inside a black hole, that shape becomes extreme. At the heart of this structure lies what we call the singularity. Not a place you could point to on a map, but a breakdown in the equations themselves. Density becomes infinite. Curvature becomes infinite. The math simply stops making sense. Around this core forms the most important boundary of all, the event horizon. This is not a physical surface. You wouldn't feel it beneath your feet. There's no sudden jolt, no flash of light, no cosmic alarm. Yet crossing it changes everything. The event horizon marks the point where the escape velocity exceeds the speed of light. Beyond it, every possible path forward, every future you can have, leads deeper inward. Even standing still is no longer an option. Outside the horizon, space behaves normally. You can choose directions. You can orbit. You can turn back. Inside, space-time tilts so severely that inward becomes the same as forward in time. Just as you cannot stop tomorrow from arriving, you cannot stop falling toward the center. This is why physicists sometimes say that inside a black hole, the singularity is not a place, it's a moment. A moment in your future you cannot avoid. And this is where intuition begins to soften. Because if the singularity is inevitable in the same way tomorrow is inevitable, then asking what's inside may already be the wrong question. Inside compared to what? Compared to which observer? Compared to which definition of time? From far away, an observer never actually sees you cross the event horizon. Your image stretches, your clock slows, your light reddens and fades, frozen at the edge forever. From your perspective, nothing special happens at the horizon at all, at least not for very large black holes. No fire, no crushing force, just darkness deepening, stars disappearing, and gravity growing quieter, smoother, more absolute. Both views are correct. This isn't a trick. It's not illusion. It's the natural consequence of time flowing differently in curved space-time. And this is what makes black holes so powerful as scientific tools. They don't just hide regions of space. They force different observers to disagree about reality itself without either one being wrong. Classical physics can take us this far and no further. General relativity describes the event horizon with exquisite precision. It predicts orbits, time dilation, gravitational waves, and shadows cast against glowing gas. And every one of those predictions has been confirmed. But the moment we ask what happens after the horizon, the theory falls silent. General relativity allows a singularity, but does not explain it. It permits infinities, but cannot describe them. It predicts a destination, but not the experience of arriving there. And most troubling of all, it suggests that information might be destroyed. That suggestion is not dramatic. It's quiet, mathematical, but it strikes at the heart of physics itself. Because information is more than data. It's identity. It's history. It's what allows the universe to be consistent from one moment to the next. If black holes erase information, then two identical universes could evolve differently for no reason at all. Quantum mechanics refuses to allow that. And so, right here at the event horizon, the universe presents us with a dilemma it cannot resolve using classical ideas alone. Beyond this point, every explanation becomes speculative. Every step forward requires new rules, new intuitions, new ways of thinking about what existence even means. We've now reached a threshold. We know what a black hole looks like from the outside. We understand the boundary we cannot cross and return from. We see where classical physics ends. From here on, we enter a landscape shaped by paradox. And the first of those paradoxes, the one that haunts everything that follows, is the question of lost information. The paradox doesn't announce itself loudly. There's no explosion of logic, no obvious contradiction flashing red on a chalkboard. Instead, it arrives quietly, almost politely, hidden inside equations that work perfectly well everywhere else in the universe. It begins with a simple assumption. In quantum mechanics, information is never destroyed. This doesn't mean information is easy to recover. It doesn't mean it stays neat or readable. It can be scrambled, diluted, stretched across vast distances, but it always exists in some form. The universe, according to quantum theory, keeps perfect records. Every interaction leaves a trace. Every state evolves into another without forgetting where it came from. This principle is called unitarity, and it's not optional. Remove it, and quantum mechanics collapses. Probabilities stop adding up. Predictions lose meaning. Now place that principle next to a black hole. Imagine a book, every word, every letter encoded in atoms and energy, drifting toward a black hole's event horizon. From the outside, you watch as the book falls, slows, reddens, and fades. Eventually, its image dissolves into darkness. According to general relativity, the book passes the horizon and continues inward, inevitably crushed into the singularity. Whatever structure carried its information, atoms, particles, quantum states, is destroyed. Gone. And that is the problem. Because if the information contained in that book is truly erased, then the universe has forgotten something. The future no longer uniquely follows from the past. Two different histories could produce the same outcome. Physics breaks its promise. This tension between the smooth certainty of relativity and the strict memory of quantum mechanics is known as the black hole information paradox. It is not a philosophical puzzle. It is a technical crisis, a sign that our deepest theories cannot both be correct in their current forms. For years, many physicists assumed the answer was simple. Perhaps quantum mechanics breaks down near black holes. Perhaps information really is lost, and we must accept that the universe is not fully reversible. But that path led to strange consequences. If information can disappear in black holes, why not elsewhere? Why should the universe remember some things but forget others? What determines when the rules apply? The cracks spread quickly. Then, in the 1970s, something unexpected happened. Black holes, long thought to be perfectly black, began to glow. Stephen Hawking showed that when quantum effects are applied near the event horizon, black holes emit a faint thermal radiation, now known as Hawking radiation. Over unimaginably long timescales, this radiation causes black holes to lose mass and eventually evaporate completely. At first, this seemed like good news. If black holes disappear, then perhaps information escapes with the radiation. But the relief didn't last. Hawking radiation is random, thermal, featureless. It carries no obvious imprint of the information that fell in. If a black hole forms from a star, a book, or an entire library, the radiation looks the same. When the black hole is gone, all that remains is a warm fog of particles and no trace of what created it. The paradox deepens. Now the universe doesn't just hide information behind an event horizon. It appears to erase it entirely, leaving no record behind. For decades, physicists argued fiercely about this. Papers were written, careers were built, friendships were strained. Some insisted information must be lost. Others insisted it must escape somehow, encoded subtly in the radiation. No experiment could decide the matter, because by the time Hawking radiation becomes significant, the black hole is ancient, older than civilizations, older than planets, older than most stars. Observing it directly is beyond our reach. And yet, the paradox refuses to fade. It sits at the intersection of gravity, quantum mechanics, and time itself, quietly insisting that something essential is missing from our understanding. What makes this paradox so powerful is not that it asks a dramatic question, but that it refuses to accept easy answers. If information is lost, quantum mechanics is incomplete. If information is preserved, general relativity is hiding something. If neither is wrong, then reality is stranger than either theory admits. This is why black holes are not just astrophysical objects. They are stress tests for the laws of nature, places where theories reveal their seams. Every hypothesis about what lies beyond a black hole, wormholes, holograms, fuzzballs, bouncing universes, begins here, as an attempt to rescue information without breaking the universe, to soften a contradiction without tearing the fabric of physics apart. As we move forward, keep this paradox in mind. It is the quiet thread running through every idea that follows. The reason physicists imagine tunnels through spacetime, the reason they flatten universes into surfaces, the reason they replace singularities with something gentler, more structured, more forgiving. Because beyond the event horizon, the universe must do something with its memories. And whatever that something is, it will redefine what we mean by reality. One of the earliest ideas to emerge from this tension didn't come from imagination, but from mathematics itself. When physicists first solved Einstein's equations for black holes, they noticed something strange hiding inside the solution. A structure that looked less like an ending and more like a passage. A bridge. In the equations, space-time didn't simply collapse inward and stop. Instead, it appeared to fold back on itself, connecting two distant regions through a narrow throat. This structure became known as an Einstein-Rosen bridge, more casually called a wormhole. The idea is deceptively gentle. Rather than destroying everything that falls in, a black hole might open into another region of space-time, perhaps far away in our own universe, or perhaps somewhere else entirely. In this picture, the singularity is not a point of annihilation, but a gateway so compressed and distorted that it only appears final from one side. From the outside, nothing changes. The event horizon still behaves the same. No signal escapes, no message returns, but beyond it, space-time may continue. If that sounds like science fiction, it's worth remembering that wormholes are not inventions of storytelling. They arise naturally from the same equations that predicted black holes themselves. Equations that have been tested again and again with extraordinary precision. And yet, there's a quiet problem. Wormholes, as the mathematics describes them, are catastrophically unstable. The moment anything tries to pass through, the throat collapses faster than light could traverse it. The bridge pinches off, sealing itself shut. What remains is, once again, a singularity. To keep a wormhole open would require something exotic, a form of matter with negative energy density. Not just unusual, but fundamentally alien to everything we've observed in nature. Quantum physics does allow negative energy in tiny, fleeting amounts, but nothing remotely close to what a traversable wormhole would need. And so, for decades, wormholes sat in an uncomfortable space, mathematically elegant, physically unsupported, too fragile to function. But they refuse to disappear, because wormholes do something very important. They preserve information. If matter passes through a black hole and emerges elsewhere, then nothing is destroyed. The universe remains consistent. Quantum mechanics breathes a quiet sigh of relief. This idea gained new life much later, when physicists began to notice a deep and surprising connection. In certain quantum systems, entanglement, the invisible linking of particles across space, behaves mathematically like a wormhole. Two particles, infinitely far apart, share a hidden structure that allows them to act as one. The phrase ER equals EPR was born, suggesting that Einstein-Rosen bridges, ER, and quantum entanglement, EPR, may be two expressions of the same underlying reality. Not literal tunnels you could fly through, but deep geometric connections woven into space-time itself. In this view, black holes may not lead to distant galaxies or parallel worlds, but to regions already entangled with ours, in ways we don't yet know how to describe. The bridge isn't a shortcut, it's a relationship. Still, even in its most refined form, the wormhole idea leaves questions unanswered. Can anything pass through intact? Is the other side observable in any meaningful way? Or is the bridge purely mathematical, a ghost structure with no physical traveler? For now, the answers remain out of reach. Wormholes offer a possibility, not a solution. A hint that space-time may be more connected than it appears, but not yet a complete story. And as physicists pushed further, they began to ask a different question altogether. What if black holes don't connect distant places in our universe? What if they connect entirely different universes? As wormholes stretch space itself into bridges, another idea stretched reality even further, beyond 3 dimensions, beyond a single universe, and into a landscape far stranger than anything classical physics had imagined. This idea comes from string theory, a framework that begins with a quiet assumption that the fundamental building blocks of nature are not points, but tiny vibrating strings. Their vibrations give rise to particles, forces, and even space-time itself. But strings don't live comfortably in 4 dimensions. To work at all, the mathematics requires extra dimensions, hidden directions curled up so tightly that we never notice them. And within those higher dimensions exist vast, floating structures known as brains, short for membranes. In this picture, our entire universe may be nothing more than a 3-dimensional brain drifting through a higher dimensional space. Everything we see, galaxies, stars, atoms, is confined to this surface, while gravity alone can leak into the extra dimensions. Now, place a black hole into that setting. Some physicists began to wonder whether black holes, especially the supermassive ones anchoring galaxies, might be more than gravitational sinks. They could be points where our brain touches, folds into, or even collides with another. In this view, falling into a black hole wouldn't mean entering a deeper region of our universe at all. It would mean slipping off our universe. The singularity then is not an end, but a contact point, a place where dimensions intersect, a seam between realities. This idea gains weight when applied to the beginning of everything. In certain brain cosmology models, the Big Bang itself is not the creation of space and time from nothing, but the result of a collision between brains. The tremendous energy released in that encounter appears from within one brain as an expanding universe. If that's true, then the birth of our cosmos may resemble the interior of a black hole seen from the outside. Suddenly, the question becomes deeply unsettling. What if every black hole is a miniature Big Bang? Not for us, but for something else. From our perspective, matter falls in and disappears. From the other side, an entire universe could be igniting. Time flows differently across dimensions. What looks like eternal collapse here could look like explosive creation there. And information, once again, is preserved, just not where we expect it to be. Of course, this idea is breathtakingly speculative. We have no experimental access to extra dimensions, no direct evidence of brains, no way to observe what lies beyond a dimensional boundary. But the mathematics is consistent, and consistency matters. It allows physicists to build models where black holes obey quantum rules without tearing space-time apart, where singularities soften into transitions, where endings become beginnings. Yet there is a price. If black holes open into other universes, then the universe is no longer a closed system. Information escapes, not destroyed, but exported. Physics remains intact, but only by expanding its definition of everything. Some find this elegant, others find it unsettling, because if black holes connect to other universes, then our universe may itself be the interior of something else's black hole. A thought that turns cosmology inside out. Still, even this grand vision has limits. It relies heavily on string theory, a framework rich in possibilities but poor in direct tests. Its beauty lies in equations, not observations. And so physicists kept searching for ideas that required fewer unseen dimensions and fewer assumptions. Ideas that stayed closer to what we can measure. Ideas that suggested something even more radical. That perhaps the black hole doesn't hide a new universe at all. Perhaps it hides nothing in the way we expect. There is a moment when thinking about black holes long enough, when the question quietly shifts. Instead of asking what's inside, some physicists began to ask something far more unsettling. What if there is no inside at all? This idea didn't come from mysticism or philosophy. It came from thermodynamics, the same science that governs engines, stars, and the slow cooling of the universe. In the 1970s, researchers noticed something deeply strange about black holes. They behave like objects with temperature and entropy. They obey laws that look uncannily like the laws of heat. And entropy, at its core, is a measure of information. The more entropy something has, the more microscopic information is hidden within it. For ordinary objects, entropy scales with volume. A bigger box holds more information. But black holes are different. Their entropy scales with surface area, not volume. The amount of information a black hole can contain is proportional to the area of its event horizon, not the space inside it. This was not a small detail. It was a warning. If information is stored on the surface, then maybe the interior isn't doing the storing at all. From this observation emerged the holographic principle, one of the most radical ideas in modern physics. It suggests that all the information contained within a region of space can be fully described by data encoded on its boundary, like a hologram on a flat surface that produces a three-dimensional image. In this view, a black hole is not a three-dimensional container with something hidden deep inside. It is a two-dimensional screen, a cosmic hard drive, encoding everything that ever fell toward it. Nothing passes through the horizon in the way we imagine. Everything is recorded on it. If this sounds abstract, consider how a movie works. The story feels three-dimensional, rich with depth and motion. But the actual information exists on a flat surface, a screen, a strip of film, a digital file. The depth is an illusion created by projection. According to the holographic principle, space-time itself may work the same way. Our three-dimensional universe could be a projection of information encoded on a distant boundary, perhaps at the edge of the cosmos itself. And black holes are where this principle reveals itself most clearly. When matter falls toward a black hole, it doesn't vanish into a hidden interior. Its information spreads across the event horizon, smeared into quantum patterns, scrambled but preserved. To an outside observer, the black hole absorbs information and stores it on its surface. To the falling observer, nothing unusual happens at the horizon. Reality continues smoothly. Both descriptions are true, and that duality, two incompatible descriptions that somehow coexist, is the key. In holographic models, there is no single objective story of what happens inside a black hole. Reality depends on perspective. What looks like a volume to one observer is a surface to another. The inside is not a place, it's a way of organizing information. This idea has powerful consequences. If the holographic principle is correct, then black holes do not need wormholes, extra dimensions, or new universes to preserve information. The information never leaves our universe at all. It never disappears. It is simply re-expressed. The paradox dissolves, not by adding something new, but by redefining what space actually is. But the cost is profound, because if black holes are holograms, then the universe itself may be one too. Space may not be fundamental. Time may not be fundamental. They may emerge from something deeper, a vast, invisible bookkeeping of quantum information. In that case, asking what lies beyond a black hole becomes like asking what lies behind the pixels of screen. There is no hidden room, no deeper chamber, only code, patterns, relationships. And yet, this solution leaves some physicists uneasy. It preserves information, yes. It fits beautifully with quantum theory. It avoids infinities. But it does so by abandoning the comforting idea that space is real in the way we feel it. And for some, that is too high a price. So they look for another path, one that keeps information intact without erasing the interior entirely. A path where the black hole is not empty inside, but not singular either. What if the problem isn't that black holes destroy information, and not that space is an illusion, but that we've been imagining the interior in the wrong way all along? This question led to one of the strangest and quietly elegant ideas in modern theoretical physics, the fuzzball. At first glance, the word sounds almost playful, soft, harmless, nothing like the cold, crushing finality we associate with black holes. But the idea behind it is anything but gentle. In traditional physics, a black hole has a clean structure, an event horizon on the outside, and a singularity at the center, a point where density becomes infinite and the laws of physics collapse. The fuzzball proposal, which emerges from string theory, removes that center entirely. No singularity, no empty interior, no smooth region of spacetime waiting beyond the horizon. Instead, the black hole is made entirely of tangled quantum structure, a dense, chaotic bundle of fundamental strings and brains, woven together so tightly that there is no space left inside. Every point is structure. Every point carries information. From far away, a fuzzball looks exactly like a normal black hole. Same mass, same gravity, same shadow, same behavior. But up close, the illusion breaks. There is no horizon you gently pass through, no empty region beyond. What we call the event horizon is simply the outer surface of this quantum tangle, a boundary where space-time itself ends. In this picture, when matter falls toward a black hole, it doesn't slip through into an interior region. It collides with the fuzzball surface. Its information becomes part of the tangle, absorbed and redistributed among countless microscopic degrees of freedom. Nothing is lost. Nothing passes through. Nothing reaches a singularity. The black hole is not hollow. It is full, completely. This idea has an important advantage. It resolves the information paradox without requiring holographic projections or invisible universes. Information stays local. It never disappears behind a horizon. But the cost is subtle and profound. If fuzzballs are real, then the experience of falling into a black hole is radically different from what general relativity predicts. There is no smooth crossing, no quiet continuation of space-time. Instead, quantum structure appears exactly where classical physics insists there should be nothing unusual at all. This challenges a principle physicists once trusted deeply, that space-time is calm and featureless at the horizon of a large black hole. Fuzzballs say otherwise. They suggest that quantum effects don't wait politely at the singularity. They rise up to the surface. They replace the horizon itself. Some physicists see this as a natural correction, the universe preventing infinities by filling space with structure before things break. Others are uneasy because fuzzballs imply that an observer falling into a black hole would encounter violent quantum effects right at the edge, not deep inside. The horizon would no longer be a place of peaceful passage, but a region of extreme complexity, a firewall of information. Whether this is a flaw or a feature is still debated. What matters is that fuzzballs show us something crucial. The universe may avoid contradictions not by hiding them deeper, but by refusing to create them in the first place. No singularity, no paradox, just structure all the way down. And yet, even fuzzballs assume something important, that space-time in some form still exists. But what if space-time itself is made of something even more fundamental? What if at the deepest level, space and time are not smooth at all, but granular, woven, quantized? Imagine zooming in on space itself, not on stars, not on atoms, but on the fabric beneath everything. the stage on which reality plays out. At first, space appears smooth, continuous, like a calm ocean seen from above. But what if that smoothness is an illusion? What if, at the smallest possible scale, space is made of tiny, discrete pieces, woven together like threads in a cosmic fabric? This is the foundation of loop quantum gravity, a theory that approaches black holes from a very different direction than string theory. Instead of adding extra dimensions or new particles, it begins with a simple idea. Space-time itself is quantized. There are no infinitely small distances, no perfectly smooth curves. Space is made of loops. In this picture, gravity is not a force transmitted across space, but a consequence of how these loops are connected. The geometry of space-time emerges from an enormous network of relationships, a kind of quantum mesh that defines distance, area, and volume. And when gravity becomes extreme, as it does inside a black hole, this structure matters. In classical general relativity, collapse continues forever. Density increases without limit. Curvature diverges. A singularity forms. But loop quantum gravity forbids infinities. Just as quantum mechanics prevents electrons from spiraling endlessly into atomic nuclei, the quantization of space prevents gravitational collapse from going all the way to zero volume. At some point, the collapse must stop. And then, something remarkable happens. Instead of continuing inward, gravity changes sign. The same force that once pulled matter together becomes repulsive. Not because gravity suddenly turns off, but because the geometry of space resists further compression. The result is a bounce, a big bounce, inside the black hole. Rather than being crushed into nothingness, matter reaches a state of maximum density and then rebounds. Space expands again. Time continues, but not into our universe, into a new one. In this view, every black hole contains a seed of expansion on the other side. What looks like collapse from our perspective becomes creation from another. The interior of a black hole transforms into the beginning of a new space-time region, a universe born not from nothing, but from something that came before. The singularity disappears. In its place is a transition. This idea is both bold and strangely comforting. It suggests that the universe has a built-in mechanism for avoiding absolute endings. That when things fall too far inward, the laws of physics respond, not with destruction, but with renewal. Black holes become cosmic recycling engines. From the outside, they swallow matter and energy. From the inside, they may give rise to entire worlds. Information once again survives. It doesn't vanish. It passes through the bounce, encoded in the structure of the new universe, scrambled beyond recognition, perhaps, but preserved in principle. Of course, there's a catch. If this process is real, then the new universe is causally disconnected from ours. No signal crosses back through the bounce. No message returns from our side. The black hole remains silent and opaque. From the other side, it may look like a big bang, hot, dense, rapidly expanding. And just as we cannot see before our own cosmic beginning, observers in that universe could never see the black hole that birthed them. This idea raises profound questions. Could our universe itself be the interior of a black hole in a parent universe? Are physical constants inherited through these bounces, subtly shaping the evolution of cosmic generations? Is the universe part of a vast family tree, branching endlessly through gravitational collapse? Loop quantum gravity does not answer these questions fully, but offers something rare. A picture of black holes that is finite, coherent, and deeply quantum, without invoking hidden dimensions or exotic matter. A universe where geometry itself softens the blow, turning catastrophe into continuity. Still, like every idea we've explored so far, it remains untested, mathematically compelling, conceptually daring, experimentally distant. And so, as we step back, something becomes clear. Each theory we've explored, wormholes, brains, holograms, fuzzballs, quantum loops, is not just a different answer. It is a different way of imagining reality itself. And now, it's time to place them side by side and see what kind of picture they form together. When you step back far enough, a pattern begins to emerge. Each theory we've explored, though radically different on the surface, is responding to the same quiet demand from the universe. A demand for consistency, a refusal to accept infinities, a resistance to forgetting. They are not competing stories so much as different lenses, each sharpening one part of a picture that refuses to come fully into focus. Let's lay them gently beside one another. The wormhole idea imagines black holes as passages, not ends, but connections. Information is preserved by traveling elsewhere, hidden behind geometry too extreme for us to trace. Space folds, bridges form, and what falls and may emerge far away, or perhaps not far at all in any meaningful sense. The strength of this idea lies in its continuity. Nothing is destroyed. Reality remains whole. Its weakness is fragility. Wormholes collapse. They demand forms of matter we've never observed. They work beautifully on paper, but hesitate in nature. The brain cosmology view expands the stage entirely. Black holes become seams between universes, contact points between higher dimensional realities. Information survives by leaving our universe altogether. Here, black holes are not just astrophysical objects, they are cosmological events. Endings on one side, beginnings on another. This approach offers grandeur, but at a cost. It relies on dimensions we cannot probe and entities we cannot observe. Its elegance lives deep in abstraction. Then there is the holographic principle, which does something subtler. It doesn't send information elsewhere. It doesn't replace singularities with new structures. It redefines space. In this view, everything that appears to fall inside a black hole is already accounted for, encoded on the horizon itself. The interior is not a place that hides information, but an emergent description arising from data on a surface. This idea is powerful because it works. It preserves quantum mechanics. It avoids paradoxes. It has even been tested mathematically in simplified universes. But it asks us to give up something deeply intuitive, that space is fundamental. The fuzzball proposal takes a more physical stance. It fills the black hole with structure. No empty interior, no singularity, just quantum complexity all the way down. Information stays local. Horizons dissolve into surfaces of tangled detail. The paradox resolves by refusing to let the contradiction form in the first place. Yet fuzzballs challenge a cherished belief that crossing a horizon should be uneventful. They replace calm geometry with violent quantum texture right, where relativity predicts serenity. And finally, loop quantum gravity offers a rhythm rather than a surface. Collapse, halt, rebound. No infinities, no erasure, just transformation. Black holes become transitions. Singularities become bounces. Endings become beginnings, but not through tunnels or holograms, through the granularity of space-time itself. Each approach answers the same question differently. What happens to information? Wormholes, it travels. Brains, it escapes. Holography, it's encoded. Fuzzballs, it's absorbed. Quantum loops, it passes through. None are confirmed, and that's important because science is not choosing between fantasies. It is mapping possibilities carefully, conservatively, constrained by mathematics and consistency. These theories are not guesses. They are structured responses to a real problem. What unites them is not agreement, but direction. They all point toward a future where black holes are not paradoxes to be ignored, but guides towards something deeper, toward a framework where gravity and quantum mechanics are no longer strangers forced to share a universe, but partners speaking the same language. And yet, even with all this elegance, one uncomfortable fact remains. We cannot test these ideas directly. Not yet. Perhaps not ever. Which brings us to the next question, one that shifts the focus away from theory and toward observation. If we cannot cross a black hole, and we cannot see inside one, can we still hear what it has to say? For something that refuses to let light escape, black holes have a surprising way of making themselves known. They don't speak loudly. They don't reveal secrets directly, but they leave traces, subtle vibrations in space-time itself, and those vibrations carry hints. The first of these hints arrived not through telescopes, but through silence. In 2015, detectors on Earth felt a ripple pass through space-time, a stretching and squeezing smaller than an atom's width. It lasted less than a second, then it was gone. What caused it was unimaginably violent. Two black holes spiraling together, colliding, and merging into one. These ripples, known as gravitational waves, were predicted by Einstein a century earlier. But now they were real, measured, recorded, and listened to. And in those signals, physicists began to notice something unexpected. After the main collision, the moment of greatest violence, the newly formed black hole didn't settle instantly. It rang, like a struck bell, like a drum echoing in deep space. This phase is called the ring down. According to classical general relativity, the ring down should follow a very precise pattern. A smooth fading of vibrations, determined only by the black hole's mass and spin. But some researchers began asking a quiet question. What if the event horizon is not perfectly smooth? What if it reflects, even slightly? In certain quantum gravity models, the edge of a black hole is not an absolute absorber. Instead, it may partially reflect gravitational waves back inward, creating faint secondary echoes after the main signal. These hypothetical signals are called black hole echoes. They would be extraordinarily subtle, easy to miss, easy to confuse with noise. But if real, they would be revolutionary. Echoes would suggest structure at the horizon, something more than classical relativity allows. Perhaps quantum effects, perhaps fuzzball-like surfaces, perhaps deviations from the idea of a perfectly smooth boundary. So far, the evidence is tantalizing but inconclusive. Some analyses hint at echoes. Others find nothing beyond noise. The signals are weak, and our instruments are still learning how to listen. But the door is open. Another line of evidence comes from light itself, or rather, from its absence. When the Event Horizon Telescope turned its attention toward the center of distant galaxies, it did something extraordinary. It didn't try to photograph a black hole directly. It photographed its shadow, a dark silhouette carved out of glowing gas, bent and distorted by gravity, a shape predicted by general relativity with astonishing accuracy. These images confirm that black holes behave exactly as Einstein described, at least from the outside, but they also give us something new: precision. As these images improve, physicists can test whether the shadow's shape deviates even slightly from predictions. Tiny distortions could hint at new physics, altered horizons, quantum corrections, or exotic interiors. So far, the shadows are calm, classical, elegant, but we're only just beginning to see clearly. Then there is the quietest clue of all, one we have never directly observed. Hawking radiation. If black holes truly emit this faint glow, then they're not eternal. They change, they evaporate, and in that slow process, information must either escape or be lost. Detecting Hawking radiation from an astrophysical black hole is far beyond our current abilities. It is simply too weak. But laboratory analogs, systems that mimic event horizons using sound waves, light, or superfluids, have begun to show Hawking-like effects. They're not black holes, but they are whispers. Together, these observations form a pattern. We may never cross an event horizon. We may never see what lies beyond, but we can listen. We can watch shadows dance. We can search for echoes in the fabric of space-time. Black holes may not answer us directly, but they may leave fingerprints. And those fingerprints, slowly accumulating, may one day tell us whether horizons are smooth or structured, whether singularities exist or are replaced, whether information truly vanishes or simply hides. Still, even with all our instruments, there may be a boundary we cannot cross, not because of technology, but because of principle. And that leads us to the hardest question of all. What if some truths are not just difficult to reach, but fundamentally unreachable? There's a certain kind of silence that doesn't come from distance, but from design. Black holes are not merely hard to explore. They are constructed by the very laws of physics to keep their secrets. This is not a technological problem. It is not something better rockets, sharper telescopes, or more powerful computers can simply overcome. It is a boundary written into space-time itself. Once something crosses the event horizon, it becomes causally disconnected from the rest of the universe. No signal it sends can ever arrive. No information it carries can ever be retrieved directly. This is not a matter of patience. It is a matter of impossibility. Even light, the fastest messenger the universe allows, cannot climb back out. And if light cannot return, neither can data, nor memories, nor witnesses. Any probe we send across that boundary is lost to us forever. And even if, in some imagined future, we could send something indestructible, something immune to heat, pressure, and tidal forces, the problem would remain. The moment it crosses the horizon, communication ends. From the outside, its story stops. This leads to an uncomfortable realization. There may be no experiment, no observation, no clever trick that can ever tell us directly what happens beyond a black hole's horizon. We can infer, we can model, we can constrain possibilities, but we may never know in the way science usually demands. This forces physics into unfamiliar territory, because science is built on testability, on predictions that can be checked, falsified, repeated. Black holes challenge that foundation, not by breaking the rules, but by obeying them too well. Some physicists argue that this doesn't matter. That indirect evidence is enough. That if a theory is mathematically consistent, unifies known laws, and makes correct predictions elsewhere, we should accept its implications, even if parts of it remain forever unobservable. Others disagree. They argue that questions which cannot, even in principle, be answered experimentally may not belong to physics at all. And this is where the question subtly shifts again. Perhaps asking what is inside a black hole is like asking what is north of the North Pole. The language assumes a structure that may not exist. In a complete theory of quantum gravity, the concepts of inside and outside might dissolve. Time may no longer flow the way we expect. Space may not be something you can enter or exit. The event horizon may not hide a place, but mark the limit of description. Beyond it, the universe does not become mysterious. It becomes undefined. This is not a failure of curiosity. It is a recognition of scope. Black holes may represent the edge of where questions themselves remain meaningful. And yet, This realization does not end the story, because even if we can never cross that boundary, the attempt to understand it has already reshaped physics in profound ways. The struggle to reconcile black holes with quantum mechanics has driven new mathematics, new ideas, new ways of thinking about information, space-time, and reality itself. In trying to see what cannot be seen, we have learned how much we do not yet understand, and that perhaps is the deeper gift of black holes. They remind us that the universe does not owe us answers, only patterns. And it is in tracing those patterns, even to the edge of silence, that science finds its purpose. There is a quiet irony at the heart of black holes. They are places where physics breaks down, and yet they may be the very tools that allow physics to become whole. For more than a century, our understanding of the universe has rested on two pillars that refuse to merge. General relativity, elegant and geometric, explains gravity, planets, stars, and the large-scale structure of the cosmos. Quantum mechanics, probabilistic and precise, governs particles, atoms, and the microscopic world. Both are extraordinarily successful. Both are experimentally confirmed. And yet, when brought together, they conflict. Black holes sit exactly at the point of that conflict. They are massive enough for gravity to dominate, yet compact enough for quantum effects to matter. They demand a theory that speaks both languages at once. This is why physicists often say that black holes are not just strange objects in space. They are laboratories, not physical labs we can visit, but conceptual ones where ideas are tested to their limits. Every attempt to understand what lies beyond a black hole forces us to confront the same challenge. How do space, time, matter, and information behave when pushed to extremes? The search for an answer has already transformed physics. Ideas like entropy as information, space-time as emergent, gravity as geometry, and quantum entanglement as a structural feature of reality all gain clarity through black hole research. Even technologies we now take for granted, from GPS corrections to quantum encryption, trace part of their conceptual lineage back to questions born in relativity and quantum theory. But the deeper impact lies ahead. A complete theory of quantum gravity would not only explain black holes. It would explain the origin of the universe, the nature of space-time, and the fate of information itself. It would tell us whether time had a beginning, or whether it emerged from something more fundamental. Whether space is continuous, or woven from discrete relationships. Whether the universe is truly local, or deeply interconnected in ways we have only begun to glimpse. Black holes act like anchors in this search. They keep theories honest. Any proposal that fails to explain them fails outright. And slowly, something remarkable is happening. Ideas once thought incompatible are beginning to overlap. Entanglement appears tied to geometry. Information seems to shape space. Horizons behave like thermodynamic systems. Gravity begins to look less like a force and more like a consequence. It's not yet a union, but it is a courtship. The mystery of what lies beyond black holes may never be resolved in a single dramatic breakthrough. More likely, it will fade as a question, replaced by a deeper framework where the question no longer makes sense. And when that happens, black holes will not be remembered as cosmic monsters. They will be remembered as teachers, as places where the universe showed us the limits of our thinking and gently pushed us beyond them. Long before black holes were written into equations, they existed as metaphors. They appeared wherever human understanding reached its edge, places where intuition failed, where imagination took over, and where meaning became fluid. Even today, as precise as our mathematics has become, black holes still occupy that same symbolic role. They're the universe's way of reminding us that knowledge has horizons. In philosophy, black holes echo an ancient idea that there are limits not only to what we know, but to what can be known. That reality may contain regions where questions dissolve rather than receive answers. When we ask what lies beyond a black hole, we're not just asking a physical question. We are asking whether every mystery is meant to be solved, or whether some exist simply to mark the boundary between understanding and wonder. This is why black holes have such a powerful presence in science fiction. In stories, they are rarely just objects. They are thresholds, crossings, moments of transformation. In Interstellar, a black hole becomes a bridge between time and love, physics and emotion, a place where equations and human meaning intertwine. In countless novels and films, black holes serve as portals, prisons, revelations, or rebirths. These stories are not predictions. They are reflections. They reveal how deeply the idea of the black hole resonates with us. Not because it destroys, but because it conceals. Not because it ends, but because it refuses to explain itself. Science fiction allows us to step where science cannot. To imagine what lies beyond when observation stops. To explore the emotional and philosophical consequences of entering a region where causality, identity, and time no longer behave as expected. And in doing so, it highlights something important. Even if physics one day provides a complete description of black holes, even if every paradox is resolved, every equation closed, there will still be something black holes represent that equations alone cannot capture. They remind us that the universe is not obligated to be intuitive, that truth does not always arrive as clarity. That mystery is not a flaw, but a feature. For scientists, black holes are problems to be solved. For philosophers, they are limits to be contemplated. For storytellers, they are doors to transformation. And for the rest of us, quietly listening in the dark, they are invitations to humility, to curiosity, to patience. Because standing at the edge of a black hole is not about what we see beyond it. It is about recognizing where our vision ends and choosing to keep wondering anyway. As our journey begins to slow, one thing becomes clear. Black holes are not puzzles waiting for a single clever solution. They are crossroads, places where many paths meet, overlap, and sometimes quietly contradict one another. We've seen 5 broad ways of imagining what lies beyond them. Some paths turn black holes into gateways, bending space-time into tunnels or seams between universes. Others flatten them into surfaces where depth gives way to information. Some fill them with quantum structure, refusing to allow emptiness or infinity. Others let them bounce, transforming collapse into creation. Each path is incomplete on its own, but together they tell us something important. They tell us that the universe resists finality. Again and again, when our theories predict absolute endings, singularities, infinities, erasure, deeper ideas step in to soften the blow. Space becomes emergent. Time becomes flexible. Information refuses to die. Black holes are where this resistance becomes visible. They show us that our current concepts, inside and outside, past and future, cause and effect, may be approximations, useful at human scales, but fragile under cosmic pressure. And this realization is not discouraging. It is transformative, because it suggests that the ultimate goal of physics is not to catalog objects, but to understand relationships. Not to describe what things are, but how they connect, evolve, and encode one another. In that sense, black holes are not anomalies. They're signposts. They point toward a future theory where gravity and quantum mechanics are no longer stitched together awkwardly. but arise from a single underlying structure. A theory where space-time is not assumed, but explained. Where information is not an abstract bookkeeping device, but a physical ingredient of reality. Such a theory may never describe what lies beyond a black hole in the way we imagine today. Instead, it may tell us why the question itself had to change. And when that happens, black holes will stand as the places where that change began, where physics was forced to confront its assumptions, and in doing so, outgrew them. We are not there yet, but every gravitational wave detected, every shadow measured, every paradox sharpened rather than ignored, brings us closer, not to certainty, but to coherence. And sometimes coherence is enough. In the end, there is a gentle truth hiding beneath all the equations, debates, and speculations. Black holes do not demand answers. They invite patience. From a moment they were first written into mathematics, black holes have quietly taught us the same lesson again and again. The universe does not reveal itself all at once. It reveals itself in layers, and sometimes it reveals the limits of the questions we are allowed to ask. We began this journey wondering what lies beyond a black hole. A place, a structure, a hidden chamber behind the darkest curtain in existence. But along the way, that idea softened. Beyond the event horizon, reality does not behave like a room you can enter. It behaves like a boundary of meaning, a place where familiar language, inside, outside, before, after, begins to lose its grip. What we found instead were possibilities. Black holes as bridges, black holes as surfaces, black holes as tangled quantum objects, black holes as seeds of new universes. None confirmed, none dismissed, each one a different way of listening to the same silence. And perhaps that is the most honest answer science can give right now. Not certainty, but humility. Black holes remind us that knowledge is not a straight line moving forward. It is a slow widening of perspective, a gradual acceptance that some truths are indirect, some are contextual, and some may only ever be approached asymptotically, closer and closer, without quite arriving. Yet, even if we never know what truly lies beyond a black hole, the attempt has already reshaped our understanding of everything else. It has changed how we think about information, about space and time, about beginnings and endings. It has shown us that the universe is not just made of matter and energy, but of relationships, patterns, and limits. And in that sense, black holes have already given us their gift. They have taught us how to stand at the edge of understanding without needing to cross it. Now, as our journey comes to rest, let the images soften. Imagine that distant black hole once more, not as something threatening, but as something patient, hanging quietly in the dark, unmoving, unhurried. Stars drift around it. Galaxies turn slowly. Time stretches and relaxes. Nothing needs to be solved tonight. The universe continues, whether we watch it or not. Its mysteries remain intact, gentle and unbothered by our curiosity. And that's okay. You don't need to understand everything to be part of it. You don't need answers to feel wonder. Sometimes the most peaceful thing we can do is let a question remain open, like a door left slightly ajar, letting in just enough mystery to remind us how vast the world really is. So wherever you are, allow your thoughts to drift now. Let the weight of explanations fade. Let the cosmos grow quiet again. Breathe slowly. Rest easily. And remember, even in the deepest darkness, the universe is still telling its story softly.